Good morning, dear listeners, and welcome to today's class. Today, we'll be discussing with you at length the concepts in statistics and probability called Bayes' theorem, or otherwise called Bayes' rule, or even Bayes' law. So I have Bayes' rule or theory, Bayes' theorem, or rule or law. Of course, in probability, Bayes' theorem is used to determine the probability of conditional events. Or put in another way, it is used to determine the probability of an event given prior knowledge of the conditions of other events that might be related to that particular event. That is what we do with Bayes' theorem. The focus of our class today is to determine or to drive the formula of Bayes' theorem under different conditions of events. Number one, when there are only two events, A and B, that are found in the sample space. And two, when there are only n events, ranging from A1, A2, A3, down to AN events in the sample space. But one thing must be borne in mind, that these events on the sample space are one, mutually exclusive, and two, mutually exhaustive. They are mutually exclusive when the intersection of any two events is an empty set. And two, mutually exhaustive because the union of all the events in the sample space returns the sample space. That is what we mean by being mutually exclusive and being mutually exhaustive. So we are going to start from the first one, driving the Bayes rule or formula. Only when there are two events, A and B, in the sample space. So number one condition, number one condition, number one condition. Only two events in the sample space. Please permit me to write S as the sample space. I am going to make this derivation using a Venn diagram to make it very, very clear. So let me represent my sample space now using a Venn diagram. And let that Venn diagram be drawn this way. Look at this to be my Venn diagram. This is my Venn diagram. And of course, that Venn diagram is going to be represented with a letter S, talking about what the sample space. Because only two events are discussed, this Venn diagram is going to be partitioned into two. And let me do the partition in this way. And here is my event A, and here is my event what? B. Let me say there is also another event that is superimposed on the sample space. And let that event superimposed in sample space be represented with a letter D. So I have something like a dot here. And then that is a letter D superimposed on this sample space. So how do I drive Bayes' theorem with condition like this? We are going to make the derivation using the idea of the conditional probability. So the interest is we are going to look at the conditional probability of A occurring given that this D earlier had occurred. And later, we look at the conditional probability of B occurring given that this D had occurred. And be able now to do some adjustments to arrive at what we call Bayes rule or formula. So we begin with the first one, which is this. So we talk about probability of what? A given D. Do remember that the conditional probability in one of our previous classes already had been defined as the ratio of the joint probabilities of the events involved to the probability of the event that had occurred earlier. And when we talk about joint probability in set and set theory, we are talking about the intersection of the probability of the intersection of the two events. So this is going to be expressed as this. That this is given as probability of what? A intersection what? D. All over. Probability of the event that occurred earlier is what? D. So we have P of what? Of D. We close it. Of course, you know I can say all over what? 1 to cross multiply. By saying 1 times this would imply like this. P of what? A intersection what? D is equals. This multiplied by this will give me P of what? Of D, then multiply by. Here is P of what? Of A giving D. Close it. Of course, in the first one, we looked at the probability of A given D. We can equally look for the probability of the reverse. Reverse here, I mean, is instead of saying A given D, we now look at the probability of D given A. And in that case, what I'm going to have here becomes probability of what? D given what? A is now given as. It is still going to be defined the way we define the first one. The ratio of the joint probability of a D and A all over the probability of the event that occurred earlier, which in this context had become A. So it is going to be P of what? D intersection what? A all over P of what? Of A. We close it. Then we do cross multiplication as usual. All over 1. 1 time this will give me that this implies P of what? D intersection what? A is given as, when this multiplied by this, we have P of what? A multiplied by, we have P of D giving what? Giving A. Close it. Then there is something I want to remind us. What I want to remind us quickly is, what I have here is A intersection D. What I have here is D intersection A. In sets, both of them are the same thing. If you talk about A intersection what? A intersection what? D. And you talk about what? D intersection what? A. You are talking about those elements that are contained in what? In A, which are equally contained in what? In D. If you come here and you say those elements that are contained in D, which are equally contained in the A, whatever thing you have here is what you are going to have here. So by implication, A intersection D and D intersection A mean the same thing. And if they mean the same thing, it means that their probabilities will mean the same thing. And if you watch what I have here, this is A intersection D, which is this. This is D intersection A, which is this. So if this and this are the same thing, this probability and this probability are equal. And if this probability and this probability becomes equal, it implies that this whole probability and this whole probability must be what? Equal. And in that case, we are going to write this, which of course is 2. We say, hmm, if, we say if hmm, P of what? A intersection what? D equals P of what? D intersection what? A. It implies hmm, that the whole of this quantity must be equal to the whole of this quantity. Sure? So I am going to say it implies, let me begin to write it here, that P of what? D multiplied by P of what? A giving what? D is given as P of what? A multiplied by P of D giving what? A. Close it. Now, the interest here is to make the P of A given D to stand alone, which is where we began. Probability of A given that this D, which is superimposed on this set earlier, in this sample space earlier had occurred. I'm trying to make this quantity to stand alone. We are going to divide both sides with P of what? D, which is probability of what? D. And in doing so, what I'm going to have here becomes D is all over what? P of what? Of D. And D is all over what? P of what? D. Close up the bracket. So if I cancel this and I cancel this, what is remaining becomes this one. So this implies this is P of what? A giving what? D, which is what I have here. Then this is equals. What I have here is what? P of what? A multiplied by P of what? Of D giving what? Giving A. All over P of what? Of D. There is something I want to quickly remind you, very quickly remind you. And that which I want to quickly remind you is this. You say that P of A given D is expressed like this. If P of A given D is expressed like this, it implies that if I want to talk about P of B given D, it means I will come to this formula. Anywhere I see A, I will replace with B. And by that, all this derivation that we might likely go and begin afresh with what? B, we must have arrived at that. So we just say that this equally implies that P of what? B giving what? D is given as P, here is my A. It is no longer going to be A, it becomes B. P of B multiplied by, here is P of, here is my D given, here is A, here it becomes what? D. All over P of what? Of D. So the major two formulas we have been looking out to arrive at is this and this. But there is something that I want us now to look closely. Our interest is to have a formula, be it this and be it this, that will be able to connect all these three events here, which is A, D, and B. Even though this D is superimposed on A and what and B. But then, if you check this formula, you find out that this formula only contains A and D in every expression. This formula contains only B and D in every expression. So none of them contained the three events, A, D, and B. So we need to make some little adjustment here to arrive at what we are looking for. How do we make that adjustment? If you watch the denominator here, the denominator is talking about what? P of what? D. Here it's talking about what? P of what? Of D. So we are going to be careful as we go about that. How do we be careful? If we are asked to find the probability of this D, superimposed on this sample space, one thing we can bear in mind is that this my what? D can occur with what? A. And this my D can occur with what? With B. Or rather say, A can occur with what? D. B can occur with what? D. For instance, which of course is the most common question that is asked under this bias theory. For instance, we are looking at this A as product A, and we are looking at this B as product B, coming from what? Factory A and factory B. And this A and B, Of course, it is a particular commodity. It could be plastic rubbers, it could be plastic what rubbers. Okay? Then we are talking about that this factory what A produces A plastic rubbers, factory B produces B plastic rubbers. This factory A can occur with what we call defects. It can contain defective items. This product B equally can contain defective items. So this A can occur with D and this B can occur with D. And A occurring with D in probability means A intersection what? D. And this one occurring means what? B intersection what? D. So for me to get the probability of D, first of all, I will say that this my D alone, this my D alone, D equals, D equals, I have what? A intersection what? D. Or I have what? B intersection what? Intersection A. I have something like this. Okay? We're there. And if you watch what we have here, you either put it in this way or equally you even put it in this format. This thing which I wrote here now, it's the same thing like writing it this way. It's the same thing as writing it this way. That this thing can be written as, this thing can be implied as, this is what? D intersection what? A, or we have what? B, or you have what? Here is D. We're talking about D. So this is, it can occur with D, sorry. So this is A occurring with D, this is B occurring with D. So this thing can equally be written as what? D intersection what? B. So if we convert this into probability, I will now say therefore probability of what? D now equals. Here is my A intersection D, which I said can be written as D intersection A. And if you watch, I already expressed D intersection A here. See it here. Which is given as what? P of what? A multiplied by P of D giving what? A. So which means in place of this alone, I am going to say that this is going to be probability of what? I have what? D intersection what? A. In probability, all means and. So, sorry, all means plus. Say plus. You have P of what? D intersection what? D. And I earlier had expressed this in this way. So if I want to express that in this way here now, of course, you see what I have here, P of A multiplied by this. So this thing becomes that this is P of what? A multiplied by, I have what? P of what? D giving A. Giving A. Close it. Here is plus, I have plus. Now, for you to express this one that same way, anywhere you see A, you replace with what? B. And what you are now going to have, it becomes what? P of what? B multiplied by, here is going to be P of what? D giving what? B. Now, we have been able to find the probability of D, which is often called the total probability in this Bayes theorem. Because they know that for you to find the probability of D, you are going to talk about event A and equally talk about what event what D. And do remember that our capital derivations are these, with denominator of what? D, denominator of what? Of D. So for us to complete our derivation now, we are going to let go of P of D and replace with the equivalent of what? Of P of D. Let go of P of D here and replace with the equivalent of P of D here. So you permit me to clean the top, call up this and replace it with this quantity. And by then, our derivations have ended. And we take some questions now to make what we have done so far to be very, very concrete. Thank you for your audience. And do remember to raise your concern in the comment section so that once we come across it, we address it. And equally, when you are learning, help us now to distribute the class to the rest of the people who perhaps might also be needing our classes. So permit me to clean this. So I call up the first one. The first one says that is P of what? A given D of A given D equals. Here is my P of what? A multiplied by P of what? D given A all over. I will not write P of D again. I'll write all of these because they are the same thing as P of D. So I have what? P of A multiplied by. I have P of what? D giving A plus. I come here. P of B multiplied by. I come here. P of B multiplied by P of D giving B. This is what I have here. I call up this one again. Or we have, or that P of B giving D is giving us. What do I have here? P of what? B multiplied by P of D giving B. All over. I will not write P of D again. I will write everything here, which is what is here. So I have P of what? A multiplied by P of D giving what? A plus. I have P of B multiplied by P of D giving B. This is Bayes' formulas or rules for a situation whereby we have two events on the sample space, and those two events are events A and D, with another event that is superimposed on it, D. So when we are going to go into deriving the formula for n events, where we have A1, A2, A3, this thing is going to range, this A is going to range as A1 expressed to this plus A2 expressed to this plus A3 expressed to this, and the rest of that. And that's what brings in summation in the Bayes theorem when we want to prove that a particular formula. We really want to believe that nothing is difficult in this particular thing. We equally started from driving all this till we arrive at this quantity. And we talked about driving this quantity. And then we drive our P of D, which of course becomes what we call the denominators. Okay? So permit me to clean this thing down while we take up a question solved that can make this thing very concrete. So permit me to clean. The question says, and I read. The question says, and I read with you. Question number one. Question number one. That question number one says, a factory has two plants, A and B, just like our event in the sample space, A and B. So that is the factories, A and B. A and B. They are the two factories, A and B. We go ahead. Plant A produces 40% and plant B produces 60% of certain items produced by the factory. So in this particular factory, there are two plants, A and B. Both of them are producing a particular commodity. But plant A is producing what? 40%. But plant B is producing what? 60%. Which means the probability of factory A is 40% and the probability of factory B is 60%. So I will now come here and write this way, that my P of A, my P of what? A is given as 40%. And you know that this my 40% can be given as 0.4. 0.4. The probability of this my B, according to them, is that my P of what? B is equals to 60%. And 60% of course is 0.6. And just like we said earlier about two events found in the sample space that are mutually exclusive and two mutually exhaustive, that their sum will return back the sample space. If you watch, 40% plus 60% is 100%, which in this context is looked as what? The totality of the product, which forms the sample space. Which means if you are talking about any other event, it's not that that event is, so to say, added to get a sample space, but that event occur alongside with either A or what or B. And that was why we are using that expression there, superimposed on the sample space. So we read on. They now say 25 out of 100 products produced by plant A are defective. They say 25 out of 100 products by plant A are defective. So the probability of defective items given factory A, that is how to express this. They say 25 out of 100 products by factory A are defective. Let me write it. 25 out. 25 out of 100. Factory A, defective. Let me write TF. How to express this means that the probability of defective items coming from factory what? A is 25 over 100. Okay? Which means I am going to write probability of D given, where I am using now this D to start as what? As defective. So probability of what? My D given factory A is given as 25 over 100. 25 over 100. And of course, my 25 over 100 can be written as 0.25. We move on. They now say, and 30 out of 100 products by factory B are defective. So 30 out of 100. Factory B, defective. This thing is going to be expressed as probability of defective given factory what? B is given as 30 all over 100, which is of course 0. What? 3. 0. Then they go ahead and ask me a question. The question they asked me is this. They said, number one, obtain the total probability of selecting defective item. The total probability of selecting defective item. Total, that is I. Total probability of selecting defective item. This question they asked about total probability of selecting defective item is same thing like asking somebody to find the probability of D in that Bayes theorem we have proven earlier. That is where you have a sample space. That sample space has two plants, plant A and plant what? B. And then you have an event which is defective event or defective item superimposed on this factory plant A and what? Plant B, such that product of plant A can occur with this defective and product of what? B can occur with this defective. So, and this time around they want to ask you, what is the probability that an item selected there is defective? Which is the probability of defective what? Item. And you remember that we have already proven it, and that is exactly what is at the denominator of this particular thing. That was when we had probability of D. And we said, let us go and know how to get the probability of what? Of D. And that was why that time we talked about the sample space. We talked about something like this. talked about what S as the sample space, talked about this, talked about event what A, talked about event B, which in this case is plant A, and plant B, talked about what this, which is talking about what defective, and they want us to find this P of what of D. Okay, and earlier we have already expressed that how to get this P of D is that our P of what of D is given as, we have what we call P of what A multiplied by P of what D giving what A plus P of B multiplied by P of D giving B. If you watch this, that is exactly what I have here. That is probability of factory A multiplied by the probability of defective given that is coming from factory what A plus probability of B multiplied by the probability of defective given that it is coming from plant what B. And of course, we already have this. What is the probability of A here? Probability of A here is 0.4. So I have what? 0.4 multiplied by probability of defective given that is coming from factory A. Probability of defective given that is coming from factory A is 0.25. So I have 0.25. The sign here is plus. What is the probability of my B? The probability of my B is what? Is this? 0.6. So I have what? 0.6 multiplied by. Here, the probability of what? D, given that is B, that is probability of defective given that is coming from plant B, is what? 0.3. So I have what? 0.3. If you check all this, I think it is 0.28. I've seen 0.28. Okay. That is question number I that asked me. This is how to arrive at it. Then the second question they asked me is, I read again. They say, the probability that the item selected is from plant A, given that the item is defective. The probability that the item selected is from factory A, given that the item is what? Defective. That is the probability of factory A given defective item. That's what they want us to find. So I will now come here and write what we are looking at is our II. Our II now in probability of what? Plant A given defective item. This is a pause. Do remember that we still have it on the understanding. Look at it here. That was what we tried and proved. Look at it here. So what are we going to do? What we are going to do is going to be simple. We come here. This is our P of A. P of A is what? 0.4. So we now have what? 0.4 times. What is my P of defective giving A? It is 0.25. I have what? 0.25. Finish. All over. The whole of this is the whole of this. And it is the whole of what we have evaluated. So without wasting time, we just call it under here, which is we have what? 0.28. And whatever thing here you get becomes how to arrive at this. So what is required of us to understand in Bayes' theorem is the connections between these sets that are found in the sample space alongside that event that is superimposed on it. The moment you understand their connections, you don't have a problem. How do I mean by connection? Looking at this, you're already seeing that the probability of plant A, given that superimposed event, which is being defective or not being defective D, can be expressed as this. Plant A multiplied by defective giving A all over. Whatever thing you have in this numerator is, of course, what you have in what in the denominator. The only difference here is you talk about plant A, which is what is here. You equally talk about what plant what B. So in the real sense of it, whether the event is 3, whether the event is 4, whether the event is anything, because this one we are saying that we are going to drive in our next class of when we have n event. That n event just to tell you when the number of our events is greater than 2. It could be 3, it could be 4, it could be 5, it could be anything. That's just what we mean by being an event. So in that case, even without driving it now, if you come here, once you talk about probability of A given D, and assuming we have about 3 plants, plant A, plant B, plant C, and your interest is on plant A, the numerator still retains what it is because you're talking about plant A. The only thing that is going to change the denominator, because in the denominator, you are going to talk about what? Factory A, talk about factory B, and equally talk about that factory what? C down the line. And with that, you do not have a problem in solving problems that connects that. Okay, so in the real sense of it now, let us now say that you do not have a problem much about what we have done so much today, and to help us manage the size of this class, we are going to maybe pause this class for now and continue our next class now with the proof of when we have n events and possibly solve problems under them again. Thank you very much for your audience this morning. And as we continue to make effort to serve you equally, come to our aid by spreading the class to greater number of what of persons, and the situation whereby you are having challenge, of course, you can reach us via the contact which we have already put in the YouTube channel for more discussions and classes if you so desire. Thank you very much, and stay tuned for our next class.